welcome to the NPTEL Power System Protection course. So, we have already seen the phasor estimation techniques. Now, I would like to evaluate these techniques who are good in a relative basis. So, for that we have a lecture on frequency response of phasor estimation technique. Here in this one we will apply the frequency response perspective to different phasor estimation techniques and evaluate them. So, what this frequency response of filters must have seen in while studying filters, jet transform domain, digital filtering techniques and so. So, it is our phasor estimation techniques are filtering techniques. We are working in numerically linked platform. So, these are numerical algorithms in digital techniques. So, what it says that the power system signals are distorted. Why? Events like inrush, events like transient things, momentary transient, power loopness devices introduces harmonics, and so power system elements are interconnected. So, disturbances may be happening in this element or that. So, that propagates also. So, these you can say that modulates the voltage current signals as seen by the relay at times, and furthermore during fault the current and voltage go through transient. The frequency response provides the response of filter for different frequency as input signal, which is important to assess the performance of the filter or the estimation techniques which we are of interest. Our interest is here to obtain the fundamental component faithfully from the voltage and current signals, even though they may be distorted. So, this frequency response of filter reveals the strength of the phasor estimation techniques. We will see, you can say that how we can evaluate the frequency response of different phasor estimation techniques which we have discussed. First, let us consider for one cycle DFT widely used in relaying principles. So, same 50 Hz signal, 400 Hz sampling means one cycle corresponds to 8 point. We will be discussing again for understanding of the concept. So, this is that signal, distorted signal, and we are now with a window, and the window is having n equals to 8 samples for the 400 Hz sampling rate, 50 Hz signal. So, the interval between 2 points, consecutive points and time axis is this much of time. Now, these are the set of signals. So, what we say is that we will be applying, you can say that the one cycle DFT going back these equations, where the delta theta corresponds to 2 pi n by capital N. Now, if you see this window, so this is the current sample and this is the oldest sample in this window. So, let us, you can say that we say we number the samples. So, this is 0, 1, 2, 3, 4, 5, 6 samples. So, 0, 1, 2, 3, 4, 5, 7 samples. So, this is the current sample. So, if we consider the current sample, the associated delay is 0 from here. If it corresponds to, consider this sample 6 sample, then the associated delay from the current sample is delta t. So, we have one delay delta t. This sample, third sample from this side or fifth one from this side, this sample is having 2 delays delta t plus delta t, so 2 delays and like that. So, when you reach to this one, So, you have 1, 2, 3, 4, 5, 6, 7 delays, 7 delays. So, these 7 delays means 7 into delta t as compared to the current sample, this sample, fresh sample. Now, as already we have done for the DFT computation, so for these you can say that corresponding samples we have cosine weights and the sine weights cos delta theta and sin delta theta with a negative sign. So, delta theta corresponds to this. So, these are the sets of weights we have already used, you can say that for DFT calculation earlier. So, these weights, so when you see consider these corresponding points, so these are the corresponding weights. So, now you can say that what we will do for the cosine filter and sine filters that are being used, you can say that in the one cycle DFT computation, we will have the Z transform of the cosine filter and Z transform of the sine filters. This is to compute the frequency response. So, for this one, for any frequency corresponds to omega, the cosine filter, Z transform of that will be, we have already used, you can say that. So, we will be considering that you can say that Z 0, this corresponds to no delay, that is the for this sample, the corresponding weight for the cosine filter is 1 by root 2. So, 1 by root 2, Z 1 delay. So, that corresponds to this sample, so the corresponding weight is 0, and like that. So, when you go to the 7 delays, this the corresponding weight is 1. So, this is what for the 8 you can say that samples we have the corresponding cosine filters here. So, the Z transform of the sine filters. So, we have this. So, if you see this is the current sample, no delay, the corresponds weight is 1 by root 2, then 1, then 1 by root 2 like this, and for the last samples we have 0. So, this is for the sine filters. So, that gives you can say that the Z transform of the cosine filter and sine filters. Moving forward, we see what to do with that. For the frequency response of the filters using that Z transform of the cosine and sine filters, if we substitute the Z by e to the power j omega delta t we know for this case, omega is the frequency of the corresponding input signal. So, we go on varying the input frequency. So, accordingly omega also varies, and delta t the sampling time interval. In our case, we have 400 Hz sampling. So, accordingly 1 by 400 gives you the delta t. For fundamental frequency input, let us say our botheration is that how good is the filter for the 50 Hz or the 60 Hz component. In our case, we have considered 50 Hz. So, this omega corresponds to 2 pi 50 is 100 pi. So, the cosine filter SC for this frequency 50 Hz component, we substitute that in that Z transform equation, that all these values here as you have seen in the earlier slide. Then we get, you can say that this for this case the SC 100 pi, that is for the 50 Hz, becomes equals to 1 with an angle of minus pi by 4, magnitude 1 and phase deviation of minus pi by 4. In a similar way, when you apply this same for the same 50 Hz and to that Z transform of this sine filter and substitute the values for all the 8 points, corresponding 8 points and the corresponding delays, then we get, you can say that a magnitude of 1 and angle of positive pi by 4. For cosine we got minus pi by 4, here we are getting plus pi by 4. Now, when we apply this same concept to this DC component, that is omega equals to 0, then the frequency response that from the Z transform SC 0, that the 0 corresponds to the DC, then we substitute all the values here in that Z transform equation, then we got, you can say to be 0. And similarly, for the sine also, after substituting you get the summation to be 0. So, what does it mean? It means that the cosine filter and the sine filter both, they reject the DC component 100%. They eliminate the DC component. So, if you pass any DC value through these filters, the output will be 0. Now, similarly, if we apply second harmonic signal to these filters, which we have for the one cycle DFT, the cosine or sine. So, here you can say that 2 pi into 2 into 50, this is 200 pi. Substitute the value in this H c and the H s omega. Here also it comes out to be H c equals to 0, H s equals to 0. So, this also imply that the second harmonic component is eliminated by the two filters completely. So, that means that similarly, if we extend this to 3 pi, extend it to third harmonic, fourth harmonic, and so we will see that they reject the corresponding harmonic components completely. Finally, if you go like that with different frequency components and find the corresponding magnitude response, the magnitude part, then we will consider that we plot that. So, like consider that we talk about 50 hertz, we got one magnitude with a certain angle. So, that one magnitude means whatever input signal that will be faithfully estimated by the one cycle DFT or the sine and the cosine filters. So, no 100% input, 100% output, but for other harmonic we can say that components like we talk about DC, complete rejection, second harmonic complete rejection, third harmonic complete rejection, fourth complete rejection. Note this is you can say that 400 Hz sampling. So, based on the Shannon theorems we have shown here up to the 400 divided by 200 Hz. Now, these you can say there are three plots which frequency versus the magnitude response. So, we have you can say that cosine, the black one, red one is for the sine and the blue one is for the one cycle DFT. What we see here that these are the few remarks that the all harmonic components including DC are being completely removed by these all the three filters. Sine filters suppresses high frequency component better, sine filters red one suppresses high frequency component greater than the fundamental better than the cosine filters, true, this sine filter, this cosine filters, and in between we have the one cycle DFT, but cosine filter suppresses the subharmonic, this is cosine, this is sine. So, cosine filters suppresses the subharmonic components better than the sine filter. So, this however, you see here that the subharmonic component and the interharmonic components, not the harmonics, interharmonic components will affect the one cycle DFT. That is what the frequency response plots reveal. Once again, that the subharmonic components and the interharmonic components will influence the estimation performance that of the all the three filters which we are describing here. So, with this we can say that we see that which is better and what. Note that because of the you can say that the subharmonic component part cosine filter is better than the sine. So, that is found to be more suitable including that of the decaying DC elimination also, which we will see in the next you can say that lecture, that has certain advantage over sine filters. Now, we will move forward to how good is the half cycle DFT in terms of this frequency response. So, we have instead of 8 samples now we have 4 samples. So, 0, 1, 2, 3 delays corresponding cosine weights and the sine weights, which we have already used in the half cycle DFT computation, governing equation n by 2 here, delta theta same 2 pi small n by capital N. Now, we go for the Z transform for the cosine part and the sine part. So, we have 4 points 1, 2, 3, 4, no delay for this corresponding weight is minus 1 by root 2, then 0, then 1 by root 2 and then 1. And similarly, for the sine minus 1 by root 2, minus 1, minus 1 by root 2 and then the 0. So, by substituting this we got the Z transform of these two filters, and now by similar calculations for different frequency component starting from DC, fundamental and different harmonic components, the frequency response plot for cosine, sine and the DFT half cycle DFT blue one. What the frequency response reveals? Frequency versus the magnitude plot, that the DC values will now affect the half cycle DFT performance. Agree? So, it is unable to reject the DC component as we see for the 1 cycle DFT. 1 cycle DFT completely reject the DC value, and which is not the case with half cycle DFT. And there is one important point, we now notice that half cycle DFT can do the business quicker only with 4 samples as compared to 8 samples for full cycle in this example, but compromising the accuracy. Now, for 50 hertz all are showing 1. So, all you can say that 50 hertz, if this signal only contains 50 hertz, it will be very good. That is also what we saw from the examples while computing the phasors. But if the signal contains other components including second harmonic, the corresponding half cycle DFT is not able to eliminate as we found from the 1 cycle DFT. So, that you can say that third harmonic is being eliminated, that is true, but not other harmonics, and that also we saw that interharmonics and subharmonics part also we see that the rejection by this half cycle DFT is poor as compared to the 1 cycle DFT. So, when you require accuracy or if you are concerned about accuracy, then you will prefer 1 cycle DFT over half cycle DFT, but if speed is a concern, then you may go for half cycle DFT. Now, we will extend the same frequency response concept to least square technique, and let us see here for 1 cycle data window, the similar you can say that we can go for the Z transform approach and then apply Z equals to e to the power j omega delta t. Then we will find you can say that the corresponding computations for different window, because least square estimation can be formulated, you can say that as we have seen from 2 samples to more and more, could the 8 samples also further more also. And as you know, you can say that if you have more and more samples in the window, computation burden becomes more, but accuracy becomes better. Here also we will see here, this is 1 cycle least square estimation, and the response you can say, you see it rejects the DC completely for 50 hertz component perfect 1. So, it is pretty good for fundamental. Harmonics components second, third and fourth are being eliminated. If you see this performance frequency response performance curve, these you can say that shows similar to that of the 1 cycle DFT. So, they are comparable to each other, but again they are having the 1 cycle data for both the cases. So, in overall we see that the frequency response shows how good is the filters or the estimation of the fundamental component Phasor estimation technique in rejecting harmonics and DC. Frequency response is a steady state component perspective, but relay takes decision during transients. So, this study reveals that if the fall persists, then how good will be the corresponding estimation process during that transient process. 1 cycle DFT versus half cycle DFT, we saw that accuracy wise 1 cycle DFT will be preferred from the frequency response perspective, and that is what also during transient process also it is being observed. least square filter with the larger and larger window becomes better accuracy wise, but we are compromising speed advantage. So, in overall we observed that frequency response approach gives a which filters can be useful for protection decision in numerical laying. Thank you.